Hello students, welcome back to my video classes. In this video class, we are going to study limit comparison test. Already we are familiar with the geometric series test and P series test, the tests which are used to investigate the convergence or divergence of series. The next important test is limit comparison test. We will state and prove this in this class. Before going to limit comparison test, we have to know what is comparison test. We'll use comparison test in proving the theorem of limit comparison test. If summation un and summation vn are two series of non-negative terms such that there is a positive integer m and k belongs to R plus such that 0 less than or equal to un less than or equal to k times vn. If this condition is satisfied for all n greater than or equal to m and summation vn is convergent, then summation un is also convergent. So what this is saying, if summation un and summation vn are two series of non-negative terms, non-negative means if x is greater than 0, we say it is positive. If x is less than 0, we say it is negative. So if non-negative means x should not be less than 0. That means x is greater than or equal to 0. So if 0 is included, we say non-negative terms. These are non-negative terms. So x greater than or equal to 0 are non-negative terms. So x greater than 0 means they are positive terms. 0 should not be included in that. So if the series contains only non-negative terms and satisfy this condition, 0 less than or equal to un less than or equal to k times vn. So k is a positive real number. K belongs to R plus. So since it is a positive real number, I can rewrite this as un less than or equal to, if this k is taken this side, I'll get 1 by k times un less than or equal to vn. So since k is a positive real number, 1 by k is also a positive real number. So some new real number, say k1. This is also a positive real number. So we can rewrite this condition like this also. So we should not bother whether k is attached to vn or it is attached to un. We can use this theorem. What this theorem says? If summation vn is convergent, then summation un is convergent. Simply how you should remember? If vn is convergent and uns are such that uns are less than or equal to vn, then un is also, summation un is also convergent. So very important to understand, if un terms are less than or equal to vn terms and summation vn is convergent, then we say that summation un is convergent. So in the same way, the second theorem tells that if un is greater than or equal to k times vn greater than or equal to 0, this can also be written as k times un greater than or equal to vn. So in this case, if vn is divergent, summation vn is divergent, then summation un is also divergent. Means each term of un is greater than or equal to vn and summation vn is divergent, then summation un should be divergent. So for convergence, if each term is less than or equal to corresponding term of convergent sequence, then this also converges. For divergence, if each term is greater than or equal to corresponding term of divergent sequence, then summation un is also divergent. So we can use both the conditions, k times un less than or equal to vn or un less than or equal to k times vn. Here un greater than or equal to k times vn or K times Un greater than or equal to Vn. So in this case, if summation Vn is convergent, then summation Un is also convergent. In this case, if summation Vn is divergent, then summation Un is also divergent. So this comparison test we will use to prove the limit comparison test theorem. Now we are ready to prove limit comparison test. If summation Un and summation Vn are two series of positive terms, means all are greater than 0. There should not be 0 should not be included in any of the terms because we are calculating Un by Vn here. So if both are positive terms series and limit of Un by Vn is equal to L, it should be not equal to 0, then the two series summation Un and summation Vn both converge or diverge together, means both behave alike. If one is convergent, the other is convergent. If one is divergent, the other is divergent. So we have to show this in 4 cases. Means if summation Un is convergent, Vn should be convergent. If summation Un is divergent, Vn should be divergent. So again, if summation Vn is convergent, summation Un should be convergent. If summation Vn is divergent, summation Un should be divergent. These 4 cases we have to prove. So let us start the proof by taking given both are positive terms. So Un, since Un is greater than 0 and Vn is greater than 0 for all n belongs to n, because both are positive terms of series, we have Un by Vn is also greater than 0 for all n belongs to n. So we are framing a sequence Un by Vn. Since the sequence are all positive terms, the limit of this sequence, which we are calling it as L, it is greater than or equal to 0, because the sequence of positive terms, for example 1 by n, may converge to 0. So there is a possibility of getting zeros. That's why we should write greater than or equal to 0. But in the statement itself, he has given that the limit should not equal to 0. So we'll consider only greater than 0. So limit of Un by Vn is equal to L is greater than 0, since L is not equal to 0. So now we'll apply the definition of limit to the sequence, epsilon definition. So we know what is the definition. To each epsilon greater than 0, there exists a natural number n belongs to n such that modulus of Un by Vn minus L is less than epsilon for all n greater than or equal to m. So there exists m. Right? This is the definition for limit of a sequence. So in particular, this is true for every epsilon. So in particular, I am choosing let epsilon greater than 0 be such that I am choosing epsilon in such a way that L minus epsilon is still greater than 0. Why? Because our L is greater than 0. So L is to the right of 0 on the number line. So if I subtract epsilon from L, L minus epsilon is going to be on the left side to L. It may be greater than 0 or it may be less than 0. So I am choosing epsilon in such a way that L minus epsilon is greater than 0. Anyhow, L plus epsilon will be greater than 0 because it is to the right of L. So we are choosing epsilon greater than 0 in such a way that L minus epsilon is still greater than 0. So why we are choosing that, you will understand later. Okay. Also let L minus epsilon is K1 and L plus epsilon is K2. Then clearly K1 is greater than 0 and K2 is also greater than 0. So keeping aside this, so let us apply the limit definition. So to this epsilon greater than 0, since epsilon greater than 0, sorry, so for epsilon greater than 0, there exists m belongs to n such that modulus of un by vn minus L is less than epsilon for all n greater than or equal to m. So this is my definition. I am applying the definition of limit of a sequence. So if I expand this, it becomes minus epsilon less than un by vn less than plus epsilon, sorry, minus L is there here, minus L less than epsilon for all n greater than or equal to m. So adding L all the sides, we have L minus epsilon less than un by vn less than L plus epsilon for all n greater than or equal to m, right? That implies multiplying Vn all the sides. So Vn into L minus epsilon is less than Un less than again Vn into L plus epsilon. This is true for all n greater than or equal to n. And already we have assumed that L minus epsilon is K1, which is positive, and L plus epsilon is K2, which is also positive real number. So this can be written as K1 times Vn less than Un less than K2 times Vn for all n greater than or equal to m. So let us call this as 1. Now we will make use of this condition. Using this condition and limit comparison test, we will prove the 4 cases which we have discussed earlier. So what is the first case? Suppose summation un is convergent. Then we have to show that summation Vn is also convergent. So we'll consider these two parts K1 Vn less than Un for all. So let us consider these two. So K1 Vn less than Un for all n greater than or equal to m. That implies, so summation Un is convergent. So by comparison test which we have discussed earlier, from that summation Vn is also convergent. That implies by comparison test summation Vn is also convergent. So we have to show all the 4 cases like this, the rest of the 3 cases. So what is the second case? Suppose summation Un is divergent. Divergent means Vn will be divergent. If we consider these two, this is divergent and Vn's are greater than Un. So Vn is also divergent. So we'll consider these two conditions now. Un less than K2 Vn for all n greater than or equal to m. That implies by comparison test summation Vn is divergent. I'm writing in short DGT. So third case, suppose now summation Vn is convergent. So what we have to consider now, Vn is convergent. So we have to show that Un is convergent. So we'll consider these two. Un less than k2 times Vn for all n greater than or equal to m. That implies by comparison test, we have summation Un is also convergent. And finally, fourth case, suppose summation Vn is divergent. So what we have to consider here, Vn is divergent. So Uns are greater than or equal to greater than Vn. So summation Un is also divergent. So let us consider these two. K1 Vn less than Un for all n greater than or equal to m. That implies by comparison test, summation Un is also divergent. So we have shown that both behave alike. If summation Un is convergent, summation Vn is also convergent. If summation Un is divergent, summation Vn is also divergent. If summation Vn is convergent, summation Un is also convergent. If summation Vn is divergent, summation Un is also divergent. So we'll make use of this test in solving the problems. So while solving the problems, we have to calculate the limit value of Un by Vn. And we'll see if it is equal to L, then we say that both converge or diverge together. So we'll do the problems in the next class.